Welcome to our lesson today on batteries and using batteries. Okay, I'm getting a little, couldn't get my pens going. Using batteries or constructing batteries from electrochemical cells. Now, the use of a battery, first of all, what is a battery? A battery is a galvanic or voltaic cell. I've been using those kind of interchangeably. Or a series of cells. It's a cell or a series of cells used as a source of direct current. At a constant voltage. In the past, originally a battery referred to two or more cells in a series. And we'll talk about how cells in a series work in a few moments. But now it can mean any storage cell. Now, the idea is this. We have these electrochemical cells that we put together. And in the first video you saw, there are the solutions of the copper and the solutions of the copper 2+, the solution of the zinc 2+, and the metals. And they're all well and good as long as you don't need them to be portable, you don't need them to be flexible in any way. And original telegraphs actually used huge vats of those solutions underneath them to power the telegraphs. But when it comes to modern appliances, having those liquids would be kind of detrimental. It would make it difficult to hold them and transport them, and you'd have to worry about corrosion and all sorts of other things. So a lot of designs have come forward to come up with batteries. Now, there are two main classifications of batteries: primary batteries and secondary ones. Primary batteries are not rechargeable. So these are the Eveready or Copper batteries, not recharge, they're chargeable, that you'd go and buy in the store and then basically throw away when you're done. And the first one of these that came out was a dry cell from a gentleman named Leclanché. I believe that should be a capital C in there, a French scientist. And what he did was he made the electrolyte, rather than being a liquid, the electrolyte solution is a moist paste. And here we have the moist electrolytic paste. It's this blue stuff in here. And that moist paste kept everything together. It wouldn't allow sloshing or any sort of leakage, easy leakage anyway. And basically has all the things that we need. The anode is the zinc shell, and the zinc reacts with ammonia when it's oxidized to form this compound. This complex ion is called ammonium tetramine zinc. You don't need to remember the name of that. And we lose 2 electrons. And just like any other zinc being oxidized, that is a zinc 2+. On the homework, I'm going to ask you to fill in the oxidation numbers for some of the important changes. There would be no change in the ammonia. Ammonia is a neutral molecule. So the 2+ outside here means that 2+ actually applies to the zinc. At the cathode, we have this carbon rod in the middle, of the cathode. And remember the cathode, so the cathode is going up to the positive terminal. The anode, the zinc, is going to be our negative terminal for this particular battery. And at the cathode, our main reaction is that manganese is being reduced to manganese. Manganese 4 oxide is being reduced to manganese 3 oxide. And we've got some ammonium and some ammonia going on there as well. This cell, when it put together, develops a voltage of 1.5 volts. And so it's a pretty standard voltage. And that's going to be regardless of the size. So this is your typical AA, AAA, C cell, D cell. The biggest differences are going to be how much materials they hold, and that means how much current they can actually generate before they start to run down. There was a problem with this. The main problem with this is that the zinc shell, since the zinc shell oxidizes, it loses mass. Remember, the anode is losing mass. And so what can happen is, as it loses mass, it can perforate. And as it perforates, then it would start to leak. So one improvement over the zinc carbon cells, as it was called, was an alkaline cell in which the zinc metal was mixed with KOH instead of being the shell. Now what happened was the zinc KOH became a paste, and that zinc was distributed through the paste. This made for more efficient oxidation. Kinetically, there's more surface area, smaller particles, more surface area, and so this was a more efficient oxidation and a higher capacity as well. So the anode is very similar, except for instead of being involved with the ammonia like above, the zinc metal is being oxidized to zinc oxide, and that is again a 2-electron process. The same basic reaction, instead of ammonium being reduced, or being the ammonium and the ammonia, we now have water and hydroxide as the acid and the base involved in here. Look at that, acid and base chemistry in batteries. How about that? And again, we go from manganese 4+ to manganese 3+, and the cell voltage, you'll not be surprised to find out, is the same, essentially the same reactions. But now the anode is no longer the zinc metal. The anode now is in contact with a steel jacket, and that steel jacket does not perforate. It does not corrode. And everything else in here is pretty similar to what you see up above. We've got the MnO2 in the cathode, and that's connected again to the positive. The red thing up here, that's connected to the positive. And again, the anode is the negative down here. Now, these batteries are well and good, and they've served their purpose, but it's better ecologically and probably financially as well to use batteries that you can recharge, and that's what a second battery is. So secondary batteries can be recharged. And there's a lot of examples of them. If you look on the side of a rechargeable battery, it usually tells you what kind you have. There's NiCad, which is nickel cadmium. There's lithium ion batteries. Those develop a bigger voltage, and so those are usually used in other applications like cell phones and computers, where you don't need to have that compact cell that we have. And one of the more recent developments is a nickel metal hydride, or NiMH battery, and that's what you'll see on the side of the battery. The technology for these is still being developed because the metal, turns out it's important to get that metal quite right, exactly right. And it's typically an alloy of some transition metal and a lanthanoid, one of those inner transition metals in that first row. And like I said, technology is still going on to come up with just the right alloy that has just the right properties. That's why we don't have a specific metal here. Now, in this case, the anode is going to be the metal hydride. That metal hydride, where the hydride, now when I'm talking about a hydride, the oxidation number of the hydrogen is a -1. And so that's going to give the metal a positive charge. Actually, it's the opposite, the positive charge, because the metal is lower in electronegativity. Now the hydrogen has a higher electronegativity. It's going to pull the electrons away from the metal and make the metal hydride. So that's going to be the anode. And at the anode, we have this hydrogen absorbing alloy along with that metal hydride. And you can see that this is a kind of layered structure inside this battery. The specifics of the layer, of the construction of the battery are not important. I really just want you to focus in on what the reactions are and how we might just try to understand what the reactions are. You won't have to memorize them, by the way. Any reactions that I'm going to ask you about for batteries, you will get those reactions on the test. At the cathode, we have this nickel hydroxide. Or actually, it starts off with this nickel oxyhydroxide. And the oxygen has its normal 2- charge. The hydroxide has its normal negative charge. So the nickel has a +3 charge. That gets reduced to nickel hydroxide, nickel 2 hydroxide in the cell. And this develops a voltage of 1.2 volts. So it's slightly lower. And for this reason, I guess some rechargeable batteries are not usable in some applications because they don't have quite the same oomph. They don't have quite the same voltage, which is really a measure of how far, think about electrons falling from a high state to a low state, how far those electrons fall, sort of like waterfall. The height of the waterfall would be equivalent to the voltage that gets developed, and the electrons would be equivalent to the water. All right, so this is a secondary battery, and the way you recharge it, we'll talk about these kinds of cells tomorrow, is you make it into what's called an electrolytic cell. You reverse the voltage, and when you reverse the voltage, you make the anode become oxidized, and so you're going to restore that, and you make the cathode become the reduction, and again, now you will restore the anode and the cathode to their original states. Actually, you never get quite back to where you originally started, and that's why these guys have a limited lifetime. And again, there's a lot of research going into developing batteries that have longer lifetimes, have better current capacity, and don't develop a memory. I think they're pretty good now about not developing a memory of discharging, that if you only discharge them 50%, then you can never go below that becomes a limit. One of the most prevalent secondary cells is the lead acid storage battery, which is used in cars and boats and planes, any place where you need a lot of power. We'll talk about that in a moment. These are probably the closest to the original electrochemical cells because they do contain an electrolyte. They contain a liquid electrolyte, and that liquid electrolyte is actually sulfuric acid, H2SO4. This creates a problem. If you remember, H2SO4 or sulfuric acid can generate, if you're not careful with metals, acids can generate hydrogen gas. Now, frequently, these batteries will go dead. They will not be able to restart the car, and so you need to have them jump-started. And modern batteries you don't worry about this anymore, but you used to have to fill up the batteries with water and check to make sure the electrolyte had the right density, and there were devices that they sold in auto parts stores to do this. And when you jump-started it, if there was hydrogen gas present and you got a spark as you connected the jumper cables, you could ignite that hydrogen gas and cause an explosion. And unfortunately, many people received acid burns from exploding batteries because they jump-started the batteries incorrectly. So those of you who are taking driver's ed, if you've learned how to jump-start a battery, be careful. Just connect the cables in the correct order, and you should be fine. Now, this is called a lead acid storage battery because lead is the primary oxidizer and reducer. So at the anode, lead metal is going to be oxidized to lead 2+ is lead sulfate. Lead sulfate is actually a solid, and so we've got these lead lead oxide, and where's our the lead oxide is the other one. Somewhere in there, there's lead sulfate being formed and 2 electrons. And then the lead oxide, those are our cathode. So you can see we've got interspersed our anode. So we've got our negatives here and our cathodes in the middle here. And what you can see, we've got a negative, there's our negative, and there's our positive. And we connect that to the, let's see, how do they have this connected? They have this connected to the positive, they should, and then to the negative, and then that gets connected to the positive, and then to the negative. And so what we develop is this battery that's in series. Oh, by the way, the overall reaction, there's our lead sulfate again. So both reactions form lead 2 sulfate as the product. And overall, we're taking 2 different forms of lead, and you're going to fill in the oxidation numbers and see how this works. And we're going, in the homework, going to lead 2 sulfate. Again, this is rechargeable, and so we return this, we go the other direction to recharge it. In the car, there is a device that's continually recharging it. It's called the alternator. And the alternator is a little device that sits on your engine and is turned by the fan belt or the engine belt and continually recharges the battery. Because they do need, like I said, they need to have a lot of current. They're very powerful. They need to have a lot of current in order to start your car. You know, they're usually 12 volts. So each cell is 2 volts, and we have 6 of those 2 volts in series. And when you do that, that adds up to a total of 12 volts. So when we have these batteries, these cells in series, like I showed you above, the positive connected to the negative, let's go to, the positive connected to the negative, the positive connected to the negative, so that what we end up with is on one side, and this only has 3, but that's okay, you get the idea. We have an overall positive over here and an overall negative over here, and that's what you would attach your leads across, and you'd get the full voltage. 2 plus 2 plus 2 plus 2, I'm missing a 2, aren't I? One more 2 gives us 12 volts. You actually do this when you have more than one battery in an appliance. A battery that has an appliance that needs 2 batteries is actually going to take 2 1.5 volt batteries and make it into a 3 volt. Or you can have 4 1.5 volts, make it into a 6 volt battery. It turns out that 9 volt batteries, so our 9 volt, those batteries you put into smoke detectors, they used to be called transistor batteries because they were the batteries that were used in transistor radios when those were big back in the 60s. 9 volt battery, want to guess how many 1.5 volts you need? I think there is a homework question on that. If not, then we will talk about it in class, but it's pretty easy. And maybe I'll find an image of that. I have a 9 volt battery in school taken apart. I wish I could show it to you. Obviously, I can't right now. So these are batteries that are storage cells. Storage cells meaning that you have what you have, you can never get any more. You can replenish it in a secondary cell, but you can't get any more reactants on board. Bring in fuel cells. Oh, sorry, one last thing. Because of the lead, even though these lead acid stored batteries are really powerful, they're also very heavy. And so they're not practical in a lot of applications. Like you wouldn't want to have to use one of them to power something that's really portable, like a phone or a computer. Another oxidation reduction reaction takes place in what we call fuel cells. And again, a fuel cell is a galvanic reaction, just like a battery is a galvanic cell. It's a galvanic cell, but in this case, the fuel to be oxidized. So the fuel is always being oxidized, is continually supplied. Continually, that doesn't look like continually. I think I'm missing an N and a U. All right, so continually supplied, continually being replenished. And in this case, it's going to be able to replace the typical combustion reaction, a combustion engine. So in most cars that aren't electric cars, are run by internal combustion engines. Electric cars, by the way, right now are run by lithium-ion batteries. Fuel cells are different. Fuel cells would be run by hydrogen. And if you've ever seen an experimental bus that says powered by hydrogen, that might be what's going on. In this fuel cell, you have a combustion reaction, but it's carried out under controlled conditions. And these controlled conditions, things like lower temperature, that's important, make it more efficient than the combustion engine. And you're going to read the attached hydrogen fuel cells article where they'll explain a little bit more about that. In the fuel cell I've got listed to the right, hydrogen is the fuel. And so hydrogen is continually supplied to the anode. The hydrogen is being oxidized according to the first reaction. And you'll find this reaction, unlike some of the others, you'll find this reaction on chart H. And we can actually set up the electrochemical cell and the voltage for you on this one, where we've got the hydroxide. We have an electrochemical cell for the oxidation. Its reduction potential is negative 0.83 volts. So we put a negative in front of that to make it the oxidation at the anode. And so the oxidation turns the hydrogen into water. Great, we've got a lot of water coming out. At the cathode, we've got oxygen. Oxygen, this is from the air. So this is just going to be like a normal internal combustion reaction. And in between, we've got these porous carbon electrodes. So those would be graphite electrodes. And they'd be porous because what happens is they allow porous to the gases. So the hydrogen gas can get in or out. The oxygen gas can get in or out. And they contain these specific metal catalysts. And those metal catalysts are important because they help speed up the reactions. Without those catalysts, this wouldn't occur. And similar to the metal catalysts that you read about in the acid rain catalytic converters, these catalysts are made up of some expensive precious metals. So this is a little esoteric as a design for something that you're going to use in your family car. At the cathode, the oxygen gas is reduced to hydroxide, and it takes 2 waters to do that. Notice now we've got the hydroxide, 4 hydroxides going into the anode, 4 hydroxides going out at the cathode. And so hydroxide is actually being transported across that electrolyte, the hot aqueous KOH. And actually it says aqueous here. Hot aqueous. Oh, it is hot aqueous. Yeah, hot aqueous KOH. That is going to allow that hydroxide to be produced and consumed at the same time. The overall reaction, we're just burning hydrogen to make water. And for that reason, this would actually be a really great reaction to be able to do in terms of greenhouse gases because there's no carbon dioxide. But as you'll read in the article, there's other reasons why you can't, and there's other fuels that can be used. These are specialized, and they are used in spacecraft as sources of electricity and water, and that was one of the big issues on Apollo 13. They lost their oxygen tank. That's what blew. So there was nothing to mix the hydrogen with to run their fuel cells or to generate water. And so that's why they had to power things down. They didn't have enough power. They had to conserve their power until they were basically ready to get back to Earth. All right, so I hope you've enjoyed this trip through batteries. Again, the specifics of the construction of the batteries is not going to be important. The reactions are going to be important, and the things you're going to read about in the fuel cells will also be important for you to to understand. So have a great rest of your day, and we'll see you next time.